generated, fake.
That was more real to me.
You look, the sunset is more real to you, right? But that's exactly the point, that I can't tell. So I probably wouldn't answer it, but the whole point is though, how do we know when something generated is look real or not? Well, that's our, again, a sense of when we look at pictures and things like that with these arrows, we take our history of everything that we've seen, like sunsets and sunny day and the beach and the clouds, and you can actually see the water and how it's able to do the water line and everything and the clouds, and they change the shape of the clouds. Like, for all our intent and purposes, it looks pretty real. Okay? So that's why it's perception. So whenever you see about AI and the everything, don't think, why are we always only talking about perception and images? It's just easier to explain. So that's exactly why we're going to do that today. All right, so that was just perception. Being able to figure out, okay, is this sunny, is this set, and you can call it classification, you can call it object detection, but it's all basically based on visual perception system. Now, whenever you can at least perceive what something is, you go to the next stage, which is creation. And you've probably seen this style transfer results a little bit. If you haven't, we'll talk about it. So what happened here is I can take any famous painting or any scenery, and then using mathematical tools, I can get it to a different space, let's say feature space or hyperspace, where I can separate the concept of a style and the content of the image. So as soon as I can separate the style and the content of the image, then it becomes possible to recombine it from two different sources and generate this third one. Okay? So I don't know if you were able to tell here, but there aren't trees here and everything. There's more clouds, but the style is this reddish kind of thing. So this, we get the style of this distinct style of this image, and then we separate it out, get the style, and then here we get the content of this lake kind of view and the trees, and then we merge it together. Okay. So this is a natural outcrop of once we can identify and perceive things, and we can separate the two. We can separate the two from two different sources. So now I have four things I can play with. I can combine any of those two together and create it. And from mathematical point of view, it's actually really simple. You're just doing transforms from one domain to another domain. But from human perception, now all of a sudden it looks like AI or deep learning is able to create stuff.
Yeah.
So it may seem like it's a big jump, but it's really not.
Mm-hmm.
It just, you synthesize this and transform it in such a way that you get to a different domain where it's easier to combine things, subtract things, add things, just like all the mathematical operation. And then you reverse that transformation and voila. It looks like it created something. Okay, but what's the big limitation do you think here? Can an AI or a deep learning system create anything arbitrary?
Probably not.
Probably not. Why? Because it's actually depend on the inputs, right?
Yeah,
Being able to input.
Still it depends on the input and reference model, right?
Yep. So it has to have seen that style before for it to extract it correctly.
Mm-hmm.
So in this stage, it's able to do mathematics, but it's based on that, being able to go from basically a pictorial domain to a feature space, hyperspace domain to do that. And this, I call it from machine learning to deep learning kind of transition, because a lot of people, and let me take a little bit of time to talk about it since some of you seem to be interested. Traditional machine learning is the engineer has to figure out what features are interesting to them and then hand code it and then test it and figure out what kind of clustering algorithm or things that they might have, the libraries that they might have to use. So the burden of correctness is on the engineer or the data scientist, as you may, to do that. And then deep learning came along, and what it changes is that now the burden of correctness of the proof changed to the data prep side of things. So if I give it correct example, enough example, now the neural network model figures out how to extract these things and then recombine them so that it's realistic. So it's not the engineer figuring out what features we should use to recombine them. Like, oh, I wonder I should make it red or orange and identify that. No, the model figures it out automatically. So then it becomes incumbent on the engineer or the data scientist to have enough or varied examples for the neural network to generalize and do it correctly. Okay. So and that's why you're seeing the explosion now, because with the internet and everything, the number of examples we have goes from very little to a lot. And just so you know the difference, in the 60s and 70s, people who were working on DARPA was given, let's say, a battle scene and was asked to figure out enemy tanks versus things like that. Guess how many examples that they were given to make it work?
Interesting. A few times.
Huh? A few in the tens?
Yeah.
They'd be lucky. They got 2.
Whoa.
And so why do you think the first AI winter happened? Because you can't make anything work with 2. And it wasn't even labeled with ground truth. So it was fuzzy images. And so it just wasn't set up to do that. So, but then in 2012, we now got enough images and the compute to do these more interesting things. So it's a little more fundamental. And if you come from programming background, I like to use this example. Maybe not all of you know it, but we used to program in ones and zeros machine language, right? And then we went to something higher called assembly language. And then we went to higher level languages like C, and then we went to object level languages, and then now scripting languages. So you can call it all programming. So in a sense, you can call them all machine learning because it's all programming. But nobody who program in Java or C++ will say, yeah, it's the same thing as programming in machine language.
Right.
What was the key innovation that allowed me to do this high-level productivity programming language and still get the performance of a machine language? What do we use to convert it from one to another? Compiler. And deep learning. Wow, a lawyer answered compiler, so I'm really impressed. But that's exactly the key thing that's happening right now in deep learning. We now have these frameworks and things like that are acting the role of a compiler. So you can say that it's all machine learning, but really the fundamental workflow is different. And the level and the productivity that you can do is way higher now because we're, again, moving to higher level concepts of thinking. So that's just a little aside that a lot of people tend to struggle with. So we talked about that limitation, the fact that only known examples of the things that you see is able to do the style transfer. And again, the way that our innovation and everything works, if I'm able to create something, how do I now go from being able to create or combining known things to something that's a little more adaptable, a little more general? So I'm going to call that a generation. So generation is where I'm able to do something that I haven't seen before. Okay? So that's the next natural step. And here, exactly the same style transfer. There were papers from Google where they took 32 style and before. Okay, so innovation, first style transfer, it was just 1-to-1. They've seen some style, they see another one, they can transfer it. And then Google came up with like 32 to 32. You can do any mix and match of those 32. And then this kind of papers come out where using this adaptive layer, I can actually now do unseen styles that wasn't part of the training set. Right? So before that 30, it only works in that 32 that I've seen, and I only know how to extract features from that known data set. But now here, you throw any unseen style here and any content, because this adaptive layer figure out how to extract it generally, I can now generate these more, I don't want to keep using general, but more different ones. Yeah, that's what it's like. General ones, it's like, why did I screw myself by using these words? But in general, these are the progression. And I want you to see the steps of evolutions as we came from very simple perception to some creation and then generation. Okay, and the two main component that makes it work is this encoder-decoder architecture. And you'll see that a lot if you look at a lot of technical things and a lot of recent innovations. You might have seen the word autoencoder. Also, that's just an encoder plus a decoder. So we'll talk about the block diagrams before, but in general, and the biggest drawback of just autoencoder without the adaptive layers, it only works on things that I've seen. So if you add something adaptive in there, it can work on something that it doesn't see. So these encoders and decoders become architectural blocks for me to put it together in my workflow to do more spectacular things that we thought weren't possible, right? We thought that artistry was the domain of humans and the creation and generation was creative endeavor that computer can't do. Well, it turns out most of us have patterns or distinct style. As soon as you have a pattern recognizable distinct style, it becomes mathematically possible to model it, extract it, and manipulate it. So maybe the point is to be changing and not have a distinct style that people can scope you up. But that's a little bit of a thing. Okay, so here's an existential question that I like to ask. And we're going towards GANs that we all know from the title, Generative Adversarial Network. So here's the generation part, Generative Adversarial Network. So the other part that we're going to need to make a GAN work is a discriminator. So in this block diagram, we took this content, we took this style, and we created this thing. Again, the same question. How does this look to you guys? Does it look pretty realistic? Like if the artist of that style drew this skyline, it would look like this?
Yeah, quite.
So in this block diagram, where's the discriminator that's telling us whether it did a good job or a bad job?
Outside the BDD encoder that's taken input from.
No, it's not.
Huh,
That's still a generator. Again, the lawyer got it right. I think you think outside of the box.
LC?
It's us.
Ah.
It's us. So never forget the environment, which is something that engineers and things like that, when you look at the details, always forget. We're a creature of the environment, the overall system that we're interacting with. So a lot of this work, when they release and publish these results, who is the discriminator? It's the human or the whoever the judge person is. In this case, it's us in this audience.
Is that reliable though?
Huh?
I mean, will that be a reliable discriminator?
Of course it's not.
Okay, good.
Of course it's
humans are subjective.
Oh yes.
Then, yeah.
So are computers, but they're just a little less
true.
so. But the main point is there is an implicit discriminator already in this work. Meaning, when I do something, how does that researcher know something looks good? Well, because if it turns out like trees with this stuff, you know it's probably not working that well. So you have to have discrimination in a good sense. In a good sense. So discrimination in itself is not bad. It's what you do with it that's potentially good or bad, right? So there's a generation part, and then humans are acting as a discriminator part. So the obvious thing then, as I'm trying to get this narrative, is that we do something, it works, but then we take something from the environment and then we automate it or put it part of the implementation that we do. That's how we grow it one by one. So we got the generation part. So we're basically gonna mathematically define what that is. And I like to throw this up because I think it's funny because I can't understand what it's saying. And I think, what is it? Richard Feynman in physicists conference also said like we throw all this math and then nobody understand anything, including me. So I think the same thing happens in thing, and I'll tell you a little bit from academia. I think it's a big shame that in academia we hide behind a lot of math, and you think that only happens in engineering disciplines, but according to my colleagues, the same thing happened in political science, and almost all graduate work is now mathematical based. Well, I think it's good to have that systematic and, as you say, well, humans are too subjective, and then, but I think at some point we shouldn't discount our intuition and the way that we would do it. So I think the easiest way to describe a generator is it takes some input and then it's able to do something new that's plausible, fake, that you can't tell from real and fake. So what is the discriminator's job? The discriminator's job is to keep telling the generator it's fake until the discriminator can no longer tell the difference between fake and real. Then we know that it reached to the level that it kind of doesn't matter. Like then we reach the existential questions like what's real? But aside from that, that's what the discriminator's job is. And the interaction between the two of them is what makes GANs pretty hard, because let's imagine a discriminator like a God mode or a teacher mode, where you know exactly it's fake because it's like a 3-year-old trying to fake you out, right? Then that generator or 3-year-old will not be motivated enough to learn and improve. Then it basically dies, it doesn't improve. So what you really want is a discriminator and generator that learns together. So at first, discriminator is like, yeah, that looks like a pony or a unicorn. I can't tell, but just a stick figure. And then the generator is like, yeah, it's a stick figure. And then eventually they each fill in more details. Generator fills in more detail. Discriminator is able to discern more details. Like it may say, you know what, that skyline looks like your buildings doesn't work because it's curvy, because it's no longer straight. So things like that. So you want the two to grow together. And like I said, I put this up as a way of saying, you don't need all the mathematical things necessarily to understand it. You can use your intuition. And here is what a generator and discriminator is made out of. And I told you that encoder and decoder are the basic components, and that's exactly what we do. So you see this encode line with decode and the skip connections that we talked about a little bit. You see these? So it's also not just for smoothing out, but the reason you do this is because you want the picture to look real, plus all the smaller features to also transfer the style. So you want both the big picture and the small things to work together. If you don't do these, then it's going to look too distorted, potentially. So that's how you do that. And then discriminator is basically just encoding. So that's how we build it. So all these architectural components, we get them, we identify them, we put in the system workflow architecture, and then boom, comes out something cool like GANs. Okay? And this is the implementation of pix-to-pix, which is taking one picture and being able to generate another picture. And what the limitation of that from pix-to-pix is I can't take, let's say, a human and then turn it into, let's say, a building, or a completely different scene, right? It has to be somewhat analogous. Like there's a sunny picture on the beach, and then there's a sunset picture. I have a scenery picture, and then I have a slightly different scenery picture with different style. What it's not able to do is just create anything out of thin air. It has to be one-to-one translation, pix-to-pix. The vantage point is similar and things like that. So you got to understand that. Even though innovation looks like it's such a big thing, it's just doing math, using these transformations to do that. Is that pretty clear?
Yep.
Are you all on board? So, like I said, so now we took the human part, which is a discriminator, now we put it into the architecture, and now we got a GANs that works well. Okay? And the other thing we do in academia and research is that if something is a good idea, you do it again. So if one generator and one discriminator is good to create a GAN, what do? We double it. And that's how we become CycleGAN. Okay, so the name I think should make a little more sense to you. Why CycleGAN, if you didn't know before. I have 2 generators and 2 discriminators. And that's exactly what a mathematical function would say that. Let's say if I took one thing, like a black and white photo, and I, using pix-to-pix or any similar thing, I ask the generator to create a color version of it. Then, using another generator, using this color input as, color picture as the input again, if I use this generator, I should be able to get exactly the same one, right? That's what mathematical functions are good for. If I complete the loop, it should go from 1 to 1, and then the other one back to this one. And that's exactly what CycleGAN is. Why is it good? Well, because then I have mathematically provable transformation, image to image, or pix to pix, where I know I did it correctly to go from one domain to another domain. And this is just one example, but you can do so many other examples. And why the CycleGAN is a little bit more stable version of it. Okay? But in general, like I said, each of them are encoder, decoder, encoders, and then you put 2 of them together for a GAN, and then 4 of them together in a cycle like this. And from there, we can do so much more that I'll show you. But in general, this is evolution. Just block by block, we build it up. And we're just using math here to do that. Any observation or any questions about this one? Okay, so one of the things that CycleGANs get really good at is we can basically says, hey, looks like I'm making a game or some sort of thing, and I only have horses and I want to have zebras, and I don't want to draw more zebras. I say, hey, take every horse and give me a zebra version of it. Or if I have any avatar in a game or any kind of setting, graphical asset, and I have it only in day mode, and I want to go to a dark mode or a night mode, and I don't want to have to regenerate it because it's similar perspective. It says automatically generate for me, and it will do that. So that's why we call it analogous or pix to pix, because it can't be like, hey, I have a horse, give me a pig. It's much harder, right? But a horse and a zebra, good. Well, a unicorn, it's also possible. It's easy, like, but something else completely different, it's way harder. All right. So in here, I'm going to make you think a little bit again, and as I promised you, these are the 4 main thrusts that we do in AI, and especially deep learning. Even though some people get confused that reinforcement learning is not deep learning. Well, we use neural networks in there, so you can call it deep reinforcement learning. But in general, most innovation happening today is deep learning or neural network based. Okay? And let me explain to you 4 boxes, and then we'll do a little quiz to figure out if you've been paying attention or not, because can't help but assess the students as our former career pitfalls, maybe. Okay, so supervised learning. And in general, every advance that we have since 2012 tends to build off of supervised learning. Why? Because it has 1, lots of data, but 2, most importantly, is structured and labeled data. Yeah. So everything tells me what's good and what's not good, so that there's lots of examples. And what is the neural network doing? It's just basically doing curve fitting, data fitting, pattern recognition, however you understand it to do that. And if it does fit well enough and it's generalized pretty well, then anytime I give it a new data, it should be able to spit out a function or a prediction. But again, it needs a lot of data, and it's probably only going to be predict on the data that's similar enough to the data that it was shown, right? So that's supervised learning. Unsupervised learning is sort of complete opposite of it. You want the neural network to do the same thing, being able to figure out things, but the data itself is not labeled. So it's supposed to look for similarities or the patterns in the data itself, sort of categorize and group and cluster using whatever strategy it may use. And then if any new input comes in, it puts it into all the categories that it already sort of recognized. Okay, so there's big thing, supervised and unsupervised. And then there's reinforcement learning, which is exactly how we would, well, at least in Asia, teach kids, right? You do the reward punishment sort of function to do that. So the system is asked to make a decision. Based on the decision and the trajectory that it follows, there's a reward function that tells it whether it's doing well or not. And that's why games and stuff like that tends to be where the reinforcement learning research tends to happen, because 1, there's a big environment that's modeling this complex system, and there's a very easy thing that's keeping track of how well it's doing, which is the score to do that. So there are both pros and cons of that, and people are playing with more generalized rewards like curiosity and things like that, but that's a lot harder to define. But in general, as long as there's some score or reward, this system is going to optimize for that reward, and you just have to simulate enough things. And you asked about active learning. So active learning is actually now becoming a more active area of research. Because, why? Because we don't want to have millions of data for every single thing that we do. So the job of the model itself is to identify the lowest confidence area or the things that it can't quite distinguish and ask for more help to be able to distinguish or do that particular job better, and not in general. Because if you're already good, and it makes sense too, right? If you think of it from our learning perspective. Let's say I'm already good at math or arithmetic and fractions, but I'm not good at percentages. I don't want to keep practicing fractions, what I'm already good at. I want to do something else that I'm weak at, right? So, and it's a little bit like divide and conquer in a sense that, you know, you just want to get to higher overall confidence, so you want to do that targeting. Okay, so the quiz for you guys is, what does GANs or CycleGANs fit in to these 4 boxes? Is it supervised learning, unsupervised learning, reinforcement learning, or active learning? You vote supervised. Any other brave soul? Reinforcement? Remember, for reinforcement, was there a reward function?
Yeah.
In CycleGANs? Like,
Is it? I mean, I don't know. I mean, the reward is if the discriminator gives the right answer. You know, if you get the reward for the generator would be for the discriminator to say you did a good fake.
remember, we could have really dumb discriminator who were like, 6 figures? Yeah, looks like unicorn to me. Yeah, so that's the intuition. But actually, I shouldn't torture you too much. I kind of cheated. Yeah, it's actually semi-supervised or semi-unsupervised. It's not neatly in the box. It's supervised in the sense that we kind of still label things, like this is the input. It's unsupervised in the sense that it kind of, the discriminator, what its generative part, it's basically unsupervised. It's learning to do it on its own. Yeah, so, and that's why that from deep learning perspective, GANs were one of the biggest innovations because it's a path for us to go to truly unsupervised learning. So it's somewhere in there. So, but reinforcement learning is good intuition, and I actually am personally gonna think that the future is reinforcement learning, combining these things with reinforcement learning, because that's continual learning on the person on the edge. So your intuition is correct. That's where we should go. But GANs and everything, it's lacking that reward function to do that. Okay, so speaking of GANs, and now the part we talk about the recent innovation. So the GANs, because it's generating, turns out if you ask it to generate like really high resolution photos, like stick figure example, like you ask a kid to draw like actual photorealistic thing, they can't, because the skill that's required to go to like pixel correct versus some rough sketch, it's way harder. And that was one of the biggest, let's say, failings of the GANs when Ian Goodfellow came up with it a while ago. But now there's research, and big GAN, as the name implies, now they can do high resolution to do that. And many different styles, like all the categories in ImageNet, it's able to produce things in a realistic way in high resolution. So again, it's in some sense it's just an evolutionary step, but what was previously a ceiling now is no longer a ceiling. We're able to do big resolution and things like that. And then the other work that we have is you can do pics to pics, right? What's the next obvious thing to do? Video to video.
Mm-hmm.
So here you can see that here's an image segmentation where we actually label every like 26 category inside a scene, like cars, light posts, trees, everything, and every pixel basically is classified. That's what semantic segmentation is. And then you can actually just pick what kind of scenery or style that you want, like European, Asian, or whatever. And then based on this rough thing, it will actually generate a video style of it. So this is probably a little harder to see in terms of what it's doing. But so let me go to this one. This one will be a little bit easier to see. So here, we can actually change from the, these are trees and these are buildings. So the same GAN is able to output very different looking scene with the same input and then convert it to video to video. So if you just change the labels, like the whole category, and say, give me this scene, and then it's all of a sudden just changed. So that makes the content creation really easy. The other thing that it's able to do is these poses. So if you look at the media and entertainment area before, like in order to do this, they have to put like sensors over the whole body with green suits and things like that.
Yeah.
Now, the pose, they actually just analyzing the video of the input and then just generating the equivalent movement for a completely different looking person. But again, remember, this is like pics to pics, video to video. Like they can't take from a human dancing to a horse dancing. Like it doesn't work. But a human with a different style, whatever, you can convert it. Okay? So let me make sure that I get to it, to this monkey. So this is the architecture. You can dive a little bit deep into it, and you'll see that the components are the same. There's just a lot of noise injected to make sure that the things look more realistic with the trees. Turns out the branches and things like that, you have to make it look random. Like hair of people, you have to make it a little random. It can't be too deterministic or else it looks less natural. And we can cap it off that here's what MIT lists from 2017 and 18 of all the different innovations and things that are happening. Advances, and you'll see that big GANs and video to video is here in the middle here. And the other thing I wanted to highlight before we leave is we talked about only images and things like that, but BERT, the natural language processing, is bidirectional encoders with transformers, so that it's using the encoder architecture to do these things. So we're basically using these same architectural blocks and then transform it into different domains. And that's really where the power of this is going to come in. So alpha 0, things like that, it's all reinforcement learning. You all know, probably have seen lots of press on that. But in general, the 4 big thrusts that I showed you, supervised learning, unsupervised learning, reinforcement learning, and active learning is responsible for all of these. And it's being used in different combinations and using very simple architectural blocks like encoders and decoders to do them. So you can pretty much guess on how things are going to be coming. And in general, whenever we don't know, in computer science there's two tricks that we do. One, if you don't know, just try, guess. We call it random, but just guessing. It turns out it works well enough because if you do a random walk, it gets you out of bad places enough time that it works. The other is, if you don't know which one works, well, just try them all. That's what the ensemble system means. You're like, I don't know, there's 10 different ones, I don't know which ones to use. Just do them all and do some sort of averaging or some sort of total system on top of it, and then you get better results that's better than only one of them. So all of this optimization work we've been doing in graduate work for research for a long time, like 20, 30 years. But what really changed is the fact that all this millions and billions of data is available, and the GPU compute and all of this computational power is available for us to actually find patterns that before probably was a little bit impossible to do. Okay, so I think you'll get access to these slides, everything, so there's references for you to follow up. So I hope you get a pretty good flavor of the state of the art and how the AI is being approached through these vectors and what we're able to do at the beginning of 2019 with a big year ahead potentially. Thanks.
Good, very good, very good. Thank you.
Well, you can run